Right. Yeah. So, yeah, just for a little background, I'm a software engineer at Arista Networks. But before that, I was doing some side projects mainly on C and C++. Well, mainly C, let's be honest. And most of them were relating to unit testing. Some of you might remember that a few meetups before I did a talk on the C++ unit testing framework. And this is like a continuation on a other part of testing, which is basically mocking. So when I first started, my first two programming languages were Java and C. And when I really got into Java, there was this thing called Mockito, not sure if I'm pronouncing that right, but which was used to do some mocking, and I was introduced to the world of mocking through that, and I found it to be really expressive and, well, cool to use. And a few years later, when I went on to, let's say, hone my C skills, I was a bit disappointed to see that C didn't really have many choices. The main thing that was here were code generators. So let's say they would generate stubs, and you'd have to essentially call the stubs manually, which was pretty verbose and still needed some kind of like Python or other tool chain that you had to add to your own build system, which wasn't really ideal, but I get it. There were also function patchers, which essentially look for the address of the function in memory and just patch the beginning to reroute the function to some kind of stub, which I didn't find quite elegant and had some issues with it. Like pretty much all the functions were rerouted, so you had to special case between modules. And last thing that we were introduced at my school were basically dynamic linkers, because when we first did some C in my school, one of the tasks that we had was to re-implement malloc, and re-implementing malloc entailed to test on real systems. So you had to basically define a wrapper function that you would then compile into a shared library that you would then preload, and ld.so would then take over and just do the rest for you, which is great. But it's still a two-step compilation process. You have to preload the library, and yeah, it's not really ideal, but there's still the groundwork for what we want to achieve there, because let's face it, just mocking is testing interactions through the injection of something else in place of the real objects or function. So let's say you have this just simple hello world that you compile. What happens when putS is called is a little bit delicate on a health-based system with Linux. For those who are familiar, it might seem trivial, but just doing the Untitled Chapter. This essentially disassembles to that, which might just it is a pretty simple. There's some fluff plus a call to our function, but it's not really our function. It's our function at PLT, and the PLT is a like this kind of table, which contains some trampolines to our real function. And if we look at if we annotate that piece of code, then you'd see that the first thing we do when we get into the PLT is that we actually jump to an offset, to an address inside a huge table that we call the GOT, which is the global offset table. So this initially contains the address for the next instruction, which is our push Q. This, in turn, pushes the swap to resolve for a dynamic linker. And then when we get into the resolution routine, we go through the actual resolution by jumping to the resolution routine So when we get to this point, you have this idea that, well, pretty much every program here that uses dynamic linking has ways to inject whatever you want inside your running executable. So yeah, this pretty much means that we can inject whatever we want by replacing the address of the function inside the global offset table. This technique is, well, it's called, by the way, GOT poisoning, as the section said. And it turns out that this is also present in other formats, like there's a GOT on macro for macOS. And there's this thing called import descriptors on Windows PE, which is essentially the same thing, but just structured differently. So since it's like over 99% of what we want to target, we can pretty much make that cross-platform, which is what I wanted to do first. So at this point, we know that we have to replace the address, but we don't have anything to replace it with. So I'm going to address how we are going to create our stubs. And for that, we need an API. So simple stuff, we're going to make some types and a way to create and to destroy our stubs. The stub create function will take a symbol name and a function to replace the symbol with, and to destroy with simply say take the stub. So for instance, conceptually, we would like something like this. You define a function that, just as before, says no to nomm and returns null to test the interaction with malloc. You create this stub, the stub, and then call any function that uses malloc and see what happens. So stub create, for this to work, needs to actually explore every single loading module, which is done by something called rdebug, if I remember correctly. And pretty much for each loading module, you get the address of the symbol in the GOT by looking at the relocation information. So when you get that, and by doing that also for macOS and Windows, you get a way to get all of the addresses, all of the offsets in the global offset tables for each loading module for that specific symbol. We also need to make sure that when doing so, we're not actually screwing ourselves over, because if you replace malloc, but then you use malloc inside the replacement routine for malloc, things aren't going to get really well. So you have to first explore all of the loaded symbols to see, get, and store the real addresses of each of the vital functions you're going to use at the core. But then, yeah, this is pretty much everything for stubbing, but it's not near the level that we had or that Mockito has or anything else. So because stubbing is stubbing and lets you pretty much do injection however you like, but you still have to write a lot of boilerplate code to track and make some kind of mapping. So let's say if you call malloc with this argument, you should return this argument, or set no at that value, pretty much, and testing other kind of interactions, sorry. And for that, since we just have stubbing at this point, we need to add some kind of user context. So this complicates things a little bit. It's not, well, I mean, you just add an argument to a function and you make a way to retrieve your context, but it's a little bit delicate than that, because before that, you just simply replace the address by the address of your stub in the GOT and you were done. But at least it wasn't really a stub, it was mostly a replacement function. You put it in your function and it just replaces the address. So it's not really that complicated. But then here we have to also add in some kind of initialization process, which is a bit delicate because you have then to care about calling conventions, and this is a bit tricky. So yeah, at this point, the only thing left to do is to actually do that. Because if we go through assembly, you don't have to actively care about the calling convention. You just have to care about using a register, like scrap register, to store the address you want to jump to on. Well, you want to jump on. Sorry. But here, you don't actually have to care what register is set at, because then you just jump to the real function and the function takes that for you. You just have to pretty much push all of your context, well, all of the register on the stack, do your context initialization thing, then pop all the registers back, and then jump on the function. So that lets you pretty much put that away and care about that, I mean, from afar. You still have to care, but not as much as if you had to specify calling convention explicitly. So then we generate a few trampolines, and since we had some problems with ASLR and the fact that trampolines are mapped at random positions, then you have to pretty much do position independent code inside your trampoline. And that involves, well, it should involve the GOT, but we're actually hacking the GOT, so it would be a bad idea to go through the GOT again. So instead, we're just pushing the functions at the start of the trampoline, and then we get something workable of that. That's for the stubs. So for mocks, it's a little bit more fluff, let's say, on what we had with stubs. Stubs is basically the groundwork for how everything works, and mocks are basically stubs which do certain things like tracking how many times it has been called and with which parameters, and as well as returning effectively or doing some binding between parameters and return values. So let's say conceptually we have this mock, which for every size between 1 and 5 returns something, and every other size between 6 and 10 returns something else, and in the general case return null. That's essentially what the conceptual malloc mock could look like. So it's basically testing values and then returning all the values. But if you rearrange that to be a little bit more, well, first portable, because the code that I showed used some weird extension on the switch. But if we actually reorder that to make some mappings with parameters to values, storing that in a parameter map that you store inside your context that you initialized earlier, and then pretty much all that's left is just finding the right result for the parameter that you passed, and then either setting the error code appropriately or returning the right value. So as with pretty much anything in C, when you have a problem, you involve macros. So yeah, it's not that pretty, but you get the idea. You define a mock, and then you pass a name to make the types involved. Oh, I missed a semicolon there. Doing way too much code these days. So yeah, you define your types, you define your function, and then you do pretty much the same thing, but in a more, let's say, generic way. But here, we're still stuck with a return type and a parameter. So that we throw in some variadic macro parameters to add some more, let's say, yeah, pretty much to handle pretty much any functions. And we do some token detection on the first parameter to actually detect if we're going to have void. Since we can't return void, we have to make some kind of weird switch. Well, weird generation switch between the two. And the second thing that Mockito was doing is that in the function when that we had, that I showed first, if you called a function inside that context, it would actually define a binding for that function. And so it would have been pretty much enjoyable to have also that. So to do that, we'd have to also make some kind of generation switch so that we can have something that knows when we're calling the function with stub inside the context or not. And to also add to that, we throw in some complex matches. So we can, let's say, if you have malloc, you can bind any kind of size greater than 13, for example, and do that instead of specifying every value greater than 13, which would be suicide on 64. So, oh, yeah, it doesn't look really good. Yeah, that's macros for you. But the good thing with that is that you can then have things that are pretty nice for a result. So with something like this, you define a mock that will then define your function for you. You can then bind the mock to malloc and say, okay, use this blueprint that I created above. And then you can specify some interactions. So you say, hey, remember this malloc when you call that with any kind of size t, then let's say you'll return null, and let's say you'll set mem, which is pretty clean, I guess. Then you can pretty much test that, and you get the right result, everything as expected. And then you can just reset the malloc thing just to be safe, because if you return, then like Lixi might also call malloc for some reason, and it's like undefined behavior. So we just don't want to be there. Another example would be, for example, to test str.dup, which also involves malloc. So the way you would test that would be to, let's say, return a static buffer for every size less than the size of the buffer. And after that, just call the standard late str.dup and just verify the interaction that malloc has been called with a size greater or equal than the reference string, which was the hello. And yeah, verify that it was called exactly once. So this approach has a few good things. It allows you to do some per module mocking. So as I showed there, you actually target the malloc on inside the libc and nothing else. So if that function calls something in another module, it doesn't mock that call unless you do so explicitly. It's also that simple, and to be honest, the syntax is pretty sweet, at least in my opinion. On the bad things, the first thing is that you can't mock static functions because it's not going through the dynamic linker. Some might call that a caveat. Others might call that also design decisions. It's not that clear at that point. I'm mostly in the camp where of people saying that it's mostly meant to be that way, because if you try to mock static function, then the static function is an implementation detail. And if you're trying to test that, you should probably test one of the things that that function calls, or make that function not static, but with a hidden visibility, which gives you more flexibility, let's say. The second issue, which is a pretty funny one, is that compilers might decide to remove the call inside the mapping, like for this one, if you just have in the verify function or the binding function, if the function you call has no side effects, then you might decide to just remove that call, which is a pretty big gotcha. But to counter that, the mock function also returns a function pointer that you can call just for that. so it doesn't get removed because the compiler doesn't know what this function pointer is in advance. And as for the last two things, yeah, of course, OGOR macros and OGOR assembly. Macros is a pretty big thing, but so far I consider it a necessary evil. So, I mean, it could have been worse. And as for assembly, I guess it's not that bad because the trampoline code is actually really pretty simple. You don't actually do anything complex, and it's just pushing some registers, calling a function, and then popping all of those registers, and then jumping, which doesn't get really much more complex than that. The only problem is that this pretty much restricts you at a set of the set of platforms that you implemented the trampoline with. But it's trivial to port, so I guess it's not that much of a problem. So yeah, they're pretty much it. You can find the code at this GitHub repository from reaching by email and or IRC if anyone wants to have a talk on that. Any questions? Yeah. So so far there's x86. So yeah, mostly i386 and x86-64. Sorry. There's also ARM, both 32 and 64 bits, and there's a I think there's no, I don't remember. I think there's a branch with PowerPC on it, but I didn't get any hardware to test it on, so I dropped it. So yeah, pretty much all those 4 platforms. Other questions? Yeah. I'm aware there's a few companies, but I haven't done my homework before that talk, to be completely honest. But I know there's a few companies that use that. It's also pretty similar to I think it's a side project extension done by some guy on Google on Gmok. Yeah, what was Gmok? Where they also use a similar technique, but only did that for Linux, which yeah, is a shame. Any other questions? Yeah. Yeah. Yeah, I was pretty bored a few years back. Also, it's fun. Only if they're not virtual. Oh, yeah, sorry. So the question was if it would have worked with member functions of C++ classes. The answer is maybe. It works if it's not virtual. Because all non-virtual functions go through the GOT instead. I could add something to also patch the vtable of any given object, but I haven't found the time nor the documentation on that. So it's pretty much I'm pretty much leaving that for eventual let's say improvements if I get the time. Other questions? Yep. Right.